In this video, we'll take a look at applied maximum and minimum problems. And it's taking a look at how we're going to take calculus to find maximums and minimums. So we'll do the second problem first. We'll do the second example first. So let me scroll down. Second example says the altitude h in feet of a jet that goes into a dive and then again turns upward is given by the function h equals 16t to the third minus 240t squared plus 10,000, where t is the time in seconds of the dive and turn. What is the altitude of the jet when it turns up out of the dive? So if you look at the function, it's a cubic function. So our cubic function in general has either this shape to it or this shape. So in order to have a dive and a turn, it'll be the first. So how do we find, what are we looking for? What is the altitude of the jet when it turns up out of the dive? So if we knew this function, if this is the path of the jet, I'm not sure exactly what the domain is yet, then there's a dive and a turn back up. So what we're looking for is a minimum point. So if we graph this using Desmos, just so you can get a sense of what we're looking for, if we type the function into Desmos and adjust the window, then this is the path of the altitude of the jet over time. Notice it does have negative values. At time 0, the jet is at 10,000. That's the y-intercept. In this case, it's the t-intercept. So our domain is going to be t is greater than or equal to 0 because we can't have negative time. So in real applications, think about your domain. So we're not going to have any negative solutions. And the point that we're looking for is the minimum. So how do we do that using calculus? Well, if you remember from the curve sketching section, you take the derivative of our function, h prime, which would equal the derivative of 16t to the third is 48t squared. The derivative of minus 240t squared is negative 480t. The derivative of 10,000 is 0. We take our derivative and set it equal to 0 because at the maximum and minimum points, the slope of the tangent line is 0. So if we set that function equal to 0 and then solve, we're going to factor out the greatest common factor, which is 48t, and we're left with t minus 10 is equal to 0. So our two solutions are 48t is equal to 0, t minus 10 is equal to 0. So at time 0 and at time 10 seconds, the slope of the tangent line is 0. So if you take a look at the graph, that makes sense. At time, there's a maximum at 10,000, and then there's a minimum down here at 10. So after 10 seconds, we have a minimum point. The question is asking us for the altitude. What is the altitude of the jet? So we take our altitude after 10 seconds and substitute it back into h to figure out our altitude. So we would take 16 times 10 cubed minus 240 times 10 squared plus 10,000, and that's where we end up with the 2,000 feet. So these are called optimization problems. You're finding maximums or minimum values. So in this case, the domain of our function, time, had to be greater than or equal to 0 because we couldn't have negative time. So if you have a function that's already given that models the situation, how do you find a maximum or a minimum? Just like we did when we were curve sketching. Take the first derivative, set it equal to 0, find the values of your independent variable where you have a max or a min. Usually we would test it on a number line, but if we use graphing technology to help us, we can tell whether our graph has a minimum or a maximum at that point. So use graphing technology to help you determine whether that's minimum or a maximum. All right, so back to the first question. In this question, we don't have a formula, so we're going to have to find a formula. So example 1, an open box is to be made from a piece of paper that measures 8 by 10 inches by cutting a square from each of the corners and bending up the sides. Determine the side length of the square that is to be cut out so the volume of the box may be a maximum. All right, so we want to first of all determine the quantity to be maximized. Okay, well, we want the volume, we want to know the side length of the square, and we also want to know the volume is to be maximized. If possible, draw a figure illustrating the problem. So in this case, we're starting with a flat piece of paper that's 8 inches by 10. And then we're going to cut little squares out of the sides, X by X. And then we're going to take that and fold up each of the flaps. And what we'll end up with is a three-dimensional box with an open top. The bottom of this box, let's see, the width of the paper is 10 inches. So if we cut X out of each side, that's going to be 10 minus 2 times X. Along the bottom here, 8 inches. If we cut X out of each side, this is going to end up being 8 minus 2X. And if we fold up the sides of the box, the height of the box is X. So that's our drawing a figure to illustrate the problem. And then expressing the quantity, the side length of the square, as our X. So now we want to write an equation for the quantity to be maximized in terms of X. So we want the volume of the box to be maximized. So volume is equal to length times width times height. So the volume of our box is X times 10 minus 2X times 8 minus 2X. So that's the equation, the polynomial, that represents the volume of a box, depending on what side square you cut out of the corners. If you multiply that out, you end up with volume equal to 4x to the third minus 36x squared plus 80x. So just to take a look and kind of visualize what it is we're looking at, if you type it into Desmos and take a look at your 4x cubed minus 36x squared plus 80x, you've got to adjust your window so that you can see it. You can see that this polynomial that models the size x that's cut out of the side of the box. Notice as you get from 0 to 4, from 4 to 5, you have negative values for volume. So the domain of this function is only from 0 to 4. So your solution has to be somewhere in between 0 and 4. And if you look back at the physical problem, if your shortest side is 8 inches, you couldn't cut a square of size 4, because what you would end up doing is cutting the paper in half. So our domain is between 0 and 4. Okay, so the value that we're looking for. And you also notice that the maximum volume is somewhere between 0 and 4. So what we're looking for is that point. So now we're going to use calculus and then go back to the graph to make sure we're right. So how do we find a maximum? Take the derivative. So we're going to take the derivative of volume, v prime, is equal to 12x squared minus 72x plus 80. Then we're going to take that function and set it equal to 0. And then we're going to solve. So we're probably not going to be able to factor that. But I think what we could do, oh wait, I don't know where not going to be able to factor that. So what can we do? Well, see if we can get a smaller values. Everything is divisible by 4. Since we have it set equal to 0, divide both sides by 4. And we end up with 3x squared minus 18x plus 20 is equal to 0. That's not going to factor. So let's put it into quadratic formula. X equals where a is equal to 3, b is equal to negative 18, and c is equal to 20. So x equals negative b, which would be negative negative 18, plus or minus the square root of b negative 18 squared minus 4 times 3 times 20, all over 2 times 3. Simplify, we get 18 plus or minus the square root of 84 over 6. So our two answers will be 18 plus the square root of 84 over 6 and 18 minus the square root of 84 over 6. I'm going to go ahead and throw these in the calculator. So we get approximately 4.528 and approximately 1.472 as our two answers. So the answer 4.528 is not between 0 and 4, it's greater than 4. So this answer is too large to be in the domain. So we should cut out a square of approximately 1.472 inches from each side, and then fold the box up, and we'll have maximum volume. So the question was, let's make sure, determine the side length of the square that's to be cut out so the volume of the box may be a maximum. So our answer is about 1.472 inches. If they were also asked if you wanted to know the volume, then we would substitute that back into the original volume equation. So that would be the 4 times 1.472 cubed minus 36 times 1.472 squared plus 80 times 1.472. So the maximum volume, if that's what they asked for, if you take a look on Desmos, I'm going to click on the maximum value. 1.472 is the x value. 52.514 would be the maximum volume of the box. So 52.514. And that would be in cubic inches. All right, last example is another geometry type problem. We have a rectangular corral is to be enclosed with 1,600 feet of fencing. Find the maximum possible area of the corral. So if our rectangular corral, if I draw that, has a length and a width, it's to be enclosed with 1,600 feet of fencing. So if I add together around the outside, that's 1,600 feet. So 2 length plus 2w is 1,600. What we want to find, though, is the maximum possible area. If you remember from geometry, area is equal to length times width. So in order to maximize area, we have to have it all in one variable. I've got length times width, but I also know that 2 length plus 2w is equal to 1,600. So solve for either length or width. If we solve for length, we get 2 times the length equals 1,600 minus 2 times the width. Divide both sides by 2. The length is equal to 800 minus the width. So if I come over here and substitute 800 minus the width for the length times w, then that will give me an area expression, 800w minus w squared, that I can go ahead and maximize. So the area, all possible areas, are modeled by 800w minus w squared. If you remember, this is an upside down parabola, so we're looking for the maximum. What value of width and length would give us a maximum area? So we take the first derivative, a prime is equal to 800 minus 2w, set that equal to 0, we get negative 2w equals negative 800. The width would be 400. So to find the maximum area, if the width is 400, the length is 800 minus the width, which would also be 400. So the area for maximizing would be 400 times 400, which just happens to end up being 1,600 square feet. So to maximize, if you have the perimeter and you want to find maximum area, notice the most efficient ends up being a square. A square will provide you with the most area with the minimum amount of perimeter.